Hello everyone, this video is about Chapter 12, Multiple Regression. As we know, the house price is influenced by many factors, such as the area of the house, the lot size, the built year, the number of bedrooms, the number of bathrooms, and locations. In simple linear regression, what we have learned before, we only focus on one factor, such as the area of the house, to find out how this factor influenced the price of the house. Now, here we will focus on more factors, which we call multiple regression. So multiple regression is an extension of simple linear regression. Simple linear regression is a one-to-one relationship. That is, y is a dependent variable, depends on only one independent variable, x. Multiple regression is a many-to-one relationship. That is, y is a dependent variable, depends on more x, like x1, x2, x3, x4, or more. Now, let's see the model for multiple regression, which k independent variables, while y is dependent variable. x1, x2, and xk are independent variables. Beta 0, beta 1, beta 2, to beta k are called coefficient, and beta 0 is y-intercept. Similarly, as simple linear regression, we allow some unexplained error exist, so we add epsilon, which is called random error. For the random error epsilon, we also have the four assumptions as in Chapter 11, that is, 1. Mean of 0, 2. Constant variance, 3. Independent, 4. Normally distributed. We will also use the residue plot and normal probability plot to check the four assumptions. Now, let's see the methods of estimating the coefficient of the model, where y hat denotes the predicted value computed from the equation and beta I hat denote an estimator of beta I. As with simple linear regression, they are obtained by the methods of least squares, which minimize the sum of squared residue, SSE. Here is a graph of a two-variable model. It looks like a three-dimensional surface. And here is the slope for x1. Here is the slope for x2. I will continue to use the house example to show the multiple regression. For the house value, which we consider as y, and now we consider 3x variables, area in square footage, lot size, and year built. We will use the add-in data analysis in Excel, so please watch the video under project module of how to do multiple regression in Excel. Here is the Excel result using the data analysis add-in. It's very similar as how to interpret the numbers as the simple linear regression. Firstly, we look at the significant f. If significant f is smaller than 0.05, the model is significant. Here, significant f is 2.57 e negative 16, where e negative 16 is 10th negative 16 power, very small. so the model is significant. Then we look at the p-value. If p-value is smaller than 0.05, the parameter is significant. Here, the p-values for the parameters intercept x1, x2, and x3 are all smaller than 0.05, so all the parameters are significant. Under the coefficient, those are the estimators for beta 0, beta 1, beta 2, and beta 3. This one is y-intercept. And those are the slope for x1, x2, and x3. So the equation model will be y equals to negative 4623230 plus 141 times x1 plus 27 times x2 and plus 2452 times x3. So in the future, you can predict the value of y using this equation. In simple linear regression, we look at the R-square to see whether the model is reliable. For multiple regression, we looked adjusted R-square instead. It is the amount of variation explained by the regression. Here, adjusted R-square is around 87%, which means 87% of variation is explained by this model, relatively high, so the model is relatively reliable. Here is the standard error of the regression used in prediction. For multiple regression, it is more complicated than simple linear regression. We need to consider all the combinations. Here, we only focus on 3 variables, x1, x2, and x3. So we need to consider the 4 combinations, that is, y versus x1 and x2, y versus x1 and x3, y versus x2 and x3, and y versus x1, x2, and x3. Among the 4 combinations, we need to choose one as the best model, which we can use the best model to predict in the future. How to find the best model among the 4 combinations? First, the model is significant. Significant f is smaller than 0.05. 2. All the parameters are significant. All the p-values smaller than 0.05. After these 2 conditions, compare the adjusted R-square. The higher adjusted R-square, the better model will be. Here is an example. Among those 4 combinations, Model 3, the model is not significant because the significant f 0.37 is bigger than 0.05. So Model 3 is not the best model option. For Model 1, one slope is not significant, so Model 1 is not the best model option. Model 2 and Model 4, the model is significant. All the slopes are significant. Those 2 are the best model candidates. Now we compare the adjusted R-square. Model 4's adjusted R-square is 0.5721, higher than 0.5581 of the Model 2. So, Model 4 is the best model among the 4 combinations. Model 4 is the best model because model is significant. Significant F 0.000528, smaller than 0.05. 2. All the SNPs parameters are significant and higher adjusted R-square than Model 2. If all the 4 combinations are not significant, significant F bigger than 0.05, or parameters are not significant, 1 or more p-value bigger than 0.05. How to find the best model? Some suggestions. We use alpha equals to 0.05 as a standard. Significant F and p-values compared with alpha equals to 0.05. But we can increase alpha. For example, increase to 0.1, 0.2, 0.3, or even 0.4 to allow more error exist. Then significant F and p-value compared to the new alpha. If significant F is smaller than the new alpha, the model is significant now. If p-value is smaller than the new alpha, the parameters are significant now. If increase alpha, we still cannot find the best model among the 4 combinations. Maybe we can consider one of the simple linear regression model, only one x variable as the best model. Model is significant and higher R-square. How to improve the best model? By deleting all the outliers. Usually, the adjusted R-square will increase. For example, for the Y column, we have found this number is an outlier, then delete the whole row. For x1, if this number is an outlier, then delete the whole row. If this number is another outlier, then delete the whole row. For x2, if this number is an outlier, delete the whole row, and so on. For x3, if those numbers are outliers, delete the whole row. Then repeat the best model in regression. Usually, we will improve the best model because the adjusted R-square may increase. However, if deleting all the outliers, the model is not significant anymore, or some parameters are not significant anymore, that means the outliers extremely change the model. Some suggestions. 1. Increase alpha. For example, 0.1, 0.2, 0.3, or even 0.4. B. Deleting the outliers at the very beginning and do the combinations to select the best model. Or C. Keep the outliers if needed. Lastly, after we figure out the final model which we use to predict the value y in the future, we need to check the 4 assumptions. Similarly as before, we use the residue plot to check the first 3, mean of 0, constant variance, independent. For the last assumption, normally distributed, we look at the normal probability plot. We look at the residue plot. If it is overall symmetric to 0, it satisfies the assumption of mean of 0. For this example, it is not symmetric to 0, so it does not satisfy the assumption. For the second assumption, constant variance, if we can fit two parallel lines to 0, it satisfies the assumption. It is subjective, and it depends on how you argue. You can argue like this way, or this way. For the third assumption, independence, if in the residue plot there is no pattern, it does not look like anything, it satisfies the assumption. For the last assumption, normally distributed, we look at the normal probability plot to check it. If you can fit a straight line overall, it satisfies the assumption. Here, for this plot, it looks like a curve, not a straight line, so it does not satisfy the assumption. That's all for this video.